As we get into chapter 3, we're no longer going to be learning new rules for derivatives. What we're going to be doing instead is using derivatives to help us analyze different graphs and things about situations. So one of the things that we'll need to know how to do is something about critical numbers in order to analyze the different graphs and applications. So in this lesson, you'll be able to find the critical numbers of a function. Right, the first thing that we're going to be looking at when we get into chapter 3 is something that's called extrema, and extrema are just the highest and lowest values of a function, and these are y values, so how high y can get and how low y can get. And I guess you could think of these probably as kind of the range, because range are y values as well. They're just the highest and lowest values of a function. What we'll be able to use these for is if I want to maximize my profit or minimize my cost or use the least amount of material that I can, anything like that we would use extrema for. When we're looking at extrema, we're just going to do a few examples. I know I said that our target in this lesson was to find critical numbers, but I just wanted you to understand where critical numbers come from. So if I look at, it says to find the value of the derivative if it exists at each indicated extremum. And extremum just means more than one extreme value, so a high point or a low point on the graph. And again, we're talking about y values. So if you look at example 1, I have x squared minus 4x. There's a picture drawn for you. So if I'm looking at the indicated extrema, which is the point 2, negative 4, it asks me to find the value of the derivative there, and we can remember from chapter 2 that the value of the derivative is just the slope of the tangent line, and if I draw the tangent line, I notice that the derivative at that point will equal 0. Okay, then if I look at problem number 2, it's a cosine graph, and it says to find the derivative at each extremum, so they have it labeled. So at my high points and in my low points, whoops, if I draw the tangent lines at each one of those points that are listed, you'll notice once again, at each of those points, the slope is horizontal, the tangent line is horizontal, so the slope will be 0. So at each one of those, the derivative is equal to 0. And then on this last one, it's an absolute value graph. The extrema, the highest value, is 0, 4. So if I try to draw a tangent line there, we're talking about the derivative. Remember, since there's a sharp turn, we know that f prime does not exist or is undefined. And I'll just put does not exist or is undefined. We can't find the derivative at that point. So what do we notice? We notice that whenever there's a high or low point, we've either found that the derivative is going to equal 0 or the derivative is going to be undefined. So what do you notice? The value of the derivative at each of these points is either 0 or it's undefined. And we'll actually use that information to help us. If we don't have a picture, we should be able to find the highs and lows without a picture using calculus. So a critical number, let me read the definition. It says let f of x be defined at c if f prime of c equals 0. So if the derivative equals 0 or f prime of c is undefined, if the derivative is undefined, then c is a critical number of f. So what we're going to do, backing up the other way, we'll figure out where the derivative is equal to 0 or is undefined, and that's going to tell us something about the function. There's probably going to be a high point or a low point on the function. So let's just go ahead and do a few examples where we're actually finding the critical numbers. So if we want to find the critical numbers, remember again, the critical number is just either where the derivative equals 0 or where the derivative is undefined. Well, if we're going to do that, the first thing that we do need is a derivative. There are a couple ways that I could approach this problem. I could use the product rule, but I'm actually going to, just because there are no powers to go with these parentheses, I'm actually going to distribute first before I even try to take the derivative. Let's take the easiest route that we can. So if I distribute, I'll get x to the 4th minus 2x squared. So that's my function. I now would like to take the derivative, and if I take the derivative using my rules from the last chapter, I'll get 4x cubed minus 4x. All right, now if I want to find a critical number, I basically want to find where the derivative is equal to 0 or undefined. So first of all, let's figure out where my derivative will equal 0. My derivative, so I'll take my derivative and I'll set it equal to 0. And then I notice that I can factor out a 4 and an x. And when I do that, I'm going to get x squared minus 1. And then I'll get equals 0. And then I notice that I can continue factoring because that's the difference of squares, so get x plus 1 times x minus 1. And then from here, I know that my critical numbers would be x equals 0, x equals negative 1, and x equals 1. So those are all of my critical numbers. And then I'll notice there's no place where the derivative is undefined because there's no denominator in the derivative. You will notice that this is very similar to when we're finding horizontal and vertical tangent lines, because if you noticed, if the derivative was 0, then we do have a horizontal tangent line occurring there. Okay, let's look at the next example. Again, we want to find critical numbers. So again, we're going to be looking for where does the derivative equal 0, or where is the derivative undefined. Again, it's the exact same process that we follow for finding horizontal and vertical tangent lines. So this first one I notice, I'm going to use the quotient rule since I see a quotient. So I'm going to label my f and my g. My f prime would be 2, and my g prime would be 1. And now when I go to take the derivative using the quotient rule, I'll have f prime times g. So 2 times x plus 3 minus f times g prime, 2x times 1, all over g squared. And then just simplifying that a little bit, I'll get 2x plus 6 minus 2x all over x plus 3 squared. And then from here, if I simplify that, I will get 6 over x plus 3 squared. Right, and now from here, what I want to do is figure out will the derivative ever equal 0 or be undefined. First of all, looking for when it would equal 0, I would look at the numerator. Since 6 will never equal 0, we don't have a place where the derivative is equal to 0. But for undefined, I would look at where would the denominator equal 0. So I'm going to think, where would this x plus 3 squared equal 0? I really don't need the square and to consider the square, because if you think about it, I could really just square root both sides, and I'd end up just getting x plus 3 equals 0. So my critical number will occur at x equals negative 3. So they're critical numbers for either set. We don't have to differentiate between which ones they are. It's a critical number. Okay, and then example 6, f of x equals sine of x plus cosine of x. We're going to go from 0 to 2 pi. Again, we want to look for where does the derivative equal 0, or where is it undefined. So my first step is to actually find the derivative. So since there's a plus sign, we can just take the derivative of each part separately. I'll have the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. My next thing, I want to find out where does that derivative equal 0. So I'll take the derivative and set it equal to 0. And then from here, if I'm thinking, I think I'll just add sine x to both sides. So I'm going to get cosine of x is equal to sine of x. So now I just have to think, where will the cosine of x equal the sine of x? And I know at pi over 4, they're both equal to the square root of 2 over 2. So I would say that at x equals pi over 4, my values would equal the same thing. And then since this goes from 0 to 2 pi, I actually also know there's another place where they equal each other. If I look at this, I know they do equal each other at pi over 4, but they also equal each other at one of the other pi over 4s. And I know that they're both negative down here. Whoops. They're both negative down here in the third quadrant. So that would actually be at, we've got 1/4, 2/4, 3/4, 4/4. That would be at 5/4 pi. So those would be my critical numbers. I don't have to worry about my derivative being undefined because we have no fractions to worry about. So those are my critical numbers. So hopefully now you can find the critical numbers of a function.